Okay. All right, so far in this chapter, or in this section of this chapter, we talked about Hess's law. We're going to come back to Hess's law right now. But Hess basically said, when you have a set of reactants, and you turn them into a set of products, there's an enthalpy change or a heat change associated with that reaction. And it doesn't matter how many steps it takes to get from the reactants to the products, the enthalpy change will be the same. The amount of heat will be the same. So what we first started doing is doing something that we could do practically in the laboratory. We could say we could do a bunch of different reactions, measure their heat, and use those to model a reaction that we didn't even do, but we have the pieces to make those steps happen. So for instance, I gave you problems where you had multiple equations with multiple delta H's. And you arrange them in such a way that you get the reactants that you wanted, you get the products you want, you get rid of everything else. And so you're predicting what the enthalpy change will be for a reaction that you didn't even perform. You performed other reactions that let you get to it. Is that making sense? We did that. Take number 1, multiply it by 1/2. Take number 2, multiply it by -1/2. What you're doing is you're modeling an equation that you really didn't do the reaction for. Okay, so that's what Hess's law says. So we solved those kind of problems. Then yesterday, I started talking to you about something called standard enthalpies of formation. And what we said is that's what heat, or the enthalpy associated with making 1 mole of whatever substance you're talking about from its elements in their standard states. Okay? So now what we're going to do is take that a step farther and combine the two ideas. We're going to combine Hess, where the pathway doesn't matter, and we're going to combine that with standard enthalpies of formation, which are values which can be determined, recorded, and put on tables for use later. And that's what we're going to do. Okay. So let's start out with here. Consider the following pathway. Consider, because the pathway is irrelevant. Any pathway is valid. Consider, the following pathway. Consider the following. Consider the following pathway from reactants to products. Okay, we'll start out with right here, elements in the center here, in their standard states. Okay, so now all those things about elements in their standard states, so that's like all the things that are black on the periodic table, they're going to be solids. All the things that are blue are going to be liquids. All the things that are red are going to be gases. And then you have some diatomic things you got to be aware of. You got to know the 5 diatomic gases: hydrogen, nitrogen, oxygen, fluorine, chlorine. And you got to know that diatomic liquid, bromine. There are others, but those are the ones that I'm holding you for. Okay. So those are the elements in their standard states. Now we said yesterday that if you go from elements in standard state to the product. Now I'm going to write products here because it could be plural. But those were the equations that we started writing yesterday. Where we start with the elements in their standard states, and then we write an equation on how you get to the product. Now, we could also start out with reactants. And if we were to go from elements or reactants to elements in their standard states, isn't that just the reverse of the equations we wrote yesterday? Are we thinking this through? Try and process this. And this makes a lot of sense if you think about it. What I'm saying here is when we go from elements in their standard states to products, those are the equations we were starting to write yesterday. With enthalpies of formation. Delta HF prime symbol, or I should not say prime, free symbol. So you took the elements in their standard states, which you got to memorize, and you put them there based on whatever product you had. So I think, what did we have over here in our example? We had, one was NH3 over here. And so over here we put N2 and H2, and then we put in the correct coefficients. Is that ringing a bell now? So if you take the elements in their standard states and go to the products, that's the enthalpy of formation equation. And that's a value that could be looked up. Okay, they're in the back of the text. I'm going to give you the page in a couple seconds. Now what I'm saying is, let's say we imagine now we have reactants, and we go to elements in their standard states. Isn't that just the reverse of going from elements in their standard states to products? We're going from here, separate pieces building up into something. Here, separate pieces building up into something. And here we're going from something to their separate pieces. So if this is just the reverse of delta HF, enthalpy of formation, then that's just a sign change in terms of enthalpy. You flip an equation around, you change the sign, right? It's ringing a bell? I see a lot of blank stares. That's why I'm really keep needling this. I'm seeing a lot of people kind of confused. All right? So basically the pathway we're taking is we're going to say, imagine you have these reactants sitting over here, and let's say it's like a bunch of Legos. Imagine you have a Lego tower. Right? I have a Lego tower. Now I take all the Legos apart, and I rebuild them up into a Lego house. I use all the pieces. Here I had a tower, here I had a house. Well, one of the pathways to get there is to take the tower completely apart and put it back together into the house. Now, do you have to necessarily take the whole tower apart every piece by piece to get to the house? No, there's probably chunks you could use, but any pathway is valid. And if I imagine a pathway where I take everything that I have and construct it up, pull it apart into all of the individual pieces, and then build it back up, then this is the enthalpy of formation here, and this is the reverse of enthalpy of formation. That starting to make sense? Okay, okay. All right, so that's basically what we're doing. So we can say this pathway is acceptable, because any pathway is valid. Acceptable, right? Yeah. Not able. How do you spell acceptable? Go ahead.
It's AB.
Is it AB only? That's what I had in my notes. I should have just trusted myself. Hey, I was only second place in the Erie Times spelling bee in 8th grade. I did not win. I took second. It was a disappointing day in my life. This pathway is acceptable since the pathway doesn't matter. This pathway is acceptable because since the pathway doesn't matter in determining delta H for a reaction. Okay, so, and here's where, if I don't warn you, some people start freaking out and getting nervous, and relax. This is a lot easier than it's going to look. Okay, so for delta H, okay, now this is totally frozen. It's frozen for me. Oh, there it goes. All right, there you go. So, just get this down. Delta H for a reaction. Don't worry too much about the symbol here, okay? It's a delta H. Now, the delta H basically says delta H for a reaction at a standard temperature. That's what the degree sign means, okay? But it's just a delta H, and I probably won't write that degree symbol or reaction much more in the future. It's just a delta H. Okay?
What's the R times?
It's just Rxn as in reaction. So this is the change in enthalpy for a reaction. Rxn, sorry. And again, the degree symbol just means at a particular temperature, because all the values you're going to look up are based on temperature. That's going to be equal to the Greek letter this. If you're taking stats, you'd know that Greek letter. Anybody know that Greek letter?
Yeah.
What is it?
Mm-hmm.
I don't remember.
It's called sigma. Okay, this is sigma. Sigma. And I'll tell you what all these things mean in a second. N, little n. And do you remember what little n means? Moles. P is product. Delta H F degree symbol. Again, don't get overwhelmed. This is actually a lot easier than it looks. Minus sigma N of reactant and R delta H F degree symbol. And I'm going to tell you what each of these things mean. Yep.
The P is subscript.
P is a subscript, yep.
Of N.
Of N, yep. Okay, so this is change in enthalpy. Of a reaction. This right here is the Greek letter sigma.
Please put the U. Oh.
Okay, good. Yeah, that's just quotation marks. And that means the sum of. And so this is why you see this in statistics a lot of times. So like if you're taking averages or if you're taking t-tests or f-tests or things like this, you'll come across this stuff eventually. A lot of times you're summing a lot of data up. And so you just use this symbol to say you're going to add up all those things. And this is going to be moles of product. And this is going to be enthalpy of formation. And we got a sigma, and this is going to be moles of reactant. And I'm not going to relabel sigma or delta HF because I already labeled that earlier in the problem. Okay. All right, so now, standard enthalpies of formation. Standard enthalpies of formation. Delta H, F with a degree symbol. Can be found in the appendix. And you could look these up online easy too. Like if you were doing your homework and you didn't want to flip back in your book, you could just Google it. You can find it real fast. Are found in the appendix. In the back of the book, or back of the text. Starting at page A19. Now, to be quite honest, when I work on these kind of problems, I would much rather do my homework out of my textbook than do it out of my iPad. If I'm going to read some text on my iPad, I don't have a problem reading on the iPad. But the problem is when you're doing these kind of problems, you may need to go to the page for the problem. Then you're definitely going to need to go to the back of the book to see the appendix. Then you might want to go to the pages where you check your answer. And you might also want to go back into the chapter because you might need some help. And isn't that kind of difficult to do on your iPad? To flip all those different pages and bookmark them and everything like that. I think it's cumbersome. But if I have a textbook, what I would do with my textbook is personally, I would take a sticky note and put it on page 819, so whenever I want to go look up a value, I can get to it real quick. Save myself some time. So I'm going to go to my textbook now and we'll look at page 819 and see what we see there. So addition, open. So I'm going to go way to the end of the book here. There's some answers. Yeah, there's a glossary. There's up here, now we're getting into something. Okay, so these are the appendices. That's A24. That's A20. Here's A19. So this is where it starts, and there's one column there. And so right here we says, these are the substances. I've got some more substances over here. And now let's look at the next page and the next page. Do you see I have pages and pages of this stuff? Okay, so let's just look at one column here. All right. So here's the substance, and you got to be careful to pay attention to state, because there's Br2 liquid, there's Br2 gas, there's Br2 aqueous. And so they all have different enthalpies of formation. So this is enthalpy of formation in this first column. This is something called Gibbs free energy, and this is something called entropy. And those are other thermodynamic values that have to do with will things happen or not, but we're just focusing on this right now. All right, and so you're going to look at whatever the value is, that's the value. All right, so let's say we did an example. So I'm going to go back to here. All right. So let's say, delta H, F degree symbol, for elements in their standard states is 0. So delta H for elements in their standard states is 0. Now I'm going to flip back to the book again real quick to show you something. So do you notice here, remember I told you bromine is diatomic and it's a liquid? Look what its standard enthalpy of formation is, 0. And the reason is, now think about what we're talking about. We're talking about the heat associated with making something. And the thing is that this thing is just going to want to exist as Br2. So you don't have to spend any energy to make it. There's no endo or exothermic. It's just that's the way it starts. So it's not like there's no energy, but there's no formation energy. There's no energy to form it because it's already formed. It's like if you want to react something with O2. There's O2 floating all around you. You don't have to do anything to get it to the state O2 gas. It's already there. Follow that? So that's why these values are 0. Okay, so back to here. So let's do an example. Okay, so let's say calculate delta H reaction for the following. Let's say we do, again, one of my favorites, combustion of propane, C3H8, part B gas, plus 5O2 gas yields 3CO2 gas plus 4H2O gas. So I've given you a balanced equation. Okay. All right, now, our little sigma equation says delta H for the reaction is equal to the sum of. We start out with that sigma, right? Yep. Yep. All right, so now when you do this, back up to this equation. You see that equation? That's the equation we're going to exercise. What I would do is for each sigma, set them in brackets. So you're going to have 2 sets of brackets in this problem. And within each set of bracket, put each chemical in parentheses. Sign errors abound if you don't do that. So what I'm saying is, I'm going to start out with brackets, parentheses, and it says sigma N of P delta HF with the degree symbol. So what that means is you take your moles of your product times the enthalpy of formation. So for this, I'm going to start out with the products, 3 moles of CO2, 3 moles CO2 gas, times, and I'm going to go to the back of the book and look up that value. And in the back of the book, it tells me that this is negative 393.5 kilojoules per 1 mole.
Wait, how do we know there are 3 moles of CO2? Oh, never mind.
Got it?
I was looking at it.
No, that's cool. And technically that would be per mole of CO2, I guess, because I want that to cancel away. Now I'm going to close that parenthesis, and I'm going to open my parentheses again because I have another product that I'm concerned with. The other product is I have 4 moles of H2O gas. And I'm going to multiply that times its enthalpy of formation, and I'm going to move this just ever so slightly so I can make sure everything fits. Come on. Whoa, now you're getting crazy. That's just crazy. Okay. All right. So now I take my 4 moles of H2O, and this is gas. So I got to make sure that I look up the gas value because there's a liquid value too. And I look it up and I get negative 242 kilojoules per 1 mole H2O. And I'm going to close that parenthesis and close that bracket because I've done everything I need for the reactant side or product side.
So for our test, how will we know?
I'd have to provide them. And so what I would probably do is if I had to provide you, say, a value for H2O, I'd probably give you a value for H2O liquid, H2O gas, make sure you're paying attention. Okay, and then I'm going to subtract from that. So think of what that's doing now. Yep.
So if you gave us a liquid, would we have to change it?
No, I'm just saying if I gave you a liquid, you would not use that one, you would use the gas one. So you just got to use the appropriate value. Okay, now, so you notice now I'm doing a negative sign in front of everything. That takes into account flipping everything around. Back up to here. Our pathway. Here's our pathway again. Remember we said we were going to go from elements in their standard states to products? That's what we just did. We just talked about the products then. And going from elements in their standard state to products, well, that's enthalpy of formation, which the value's in the back of the book. This is the reverse, going from reactants to breaking down the elements. And so since I'm reversing that reaction, I'm putting a negative sign there to reverse all those delta H values. So here I'm going to have parentheses, I'm going to have 1 mole of C3H8 gas times its enthalpy of formation. I go look that up, and this is negative 104 kilojoules per 1 mole of C3H8 plus, because that's the sum of, 0. Why is that 0?
Because O2 is in its standard form.
It's in its standard state. Now, if you went to the back of the book and go look it up, guess what you're going to find? 0. What about a test? What did I do? Not give you anything. That's probably what I would do. I'd give you nothing, and somebody will come up to me and be like, I don't have the standard enthalpy of formation for O. I go, yep, that's right. Should I know that? Yep, you should know that. Right? It should be 0. Okay.
So how do we know when something's in its standard?
You got to know your standard states because you got to know how to write those equations.
So if it were, like, would it be possible for O2 in this equation to be like a liquid?
If it were, then it would have an enthalpy of formation
Gotcha.
because it's not in its standard state now. Correct. If it's O2 gas, standard state. It's O2 liquid, not. Okay. All right. So now let's break this down. I like just to break down one thing at a time. Okay. So I'm going to keep my brackets there, and if I do 3 times negative 393, I'm going to get negative 1180.5 kilojoules plus. If I take 4 times negative 242, I'm going to get negative 968 kilojoules. Close that out. Minus. And I'm only going to have one value here, which is negative 104 kilojoules, because it's just times 1. So now I'm going to combine the first set of, under the first set of brackets, I'm going to combine the 2 values there, and when I combine those I get negative 2148 kilojoules minus a minus 104 kilojoules, so that's actually an addition there, and so I get delta H of the reaction equal to negative 2044 kilojoules, and this is exothermic, which you would expect because it's propane being combusted. So this is not really tough. The problem is if you don't pay attention to the format, signs are going to become an issue.
So just to clarify, you
Yep.
just put the negative mole values, like the negative 1 to 4 underneath, just to save space. And it wasn't actually subtracted.
Above here,
Yeah.
like right here.
Yeah.
Yeah, because I couldn't do it all in one space. So this, what the point is this is all. Oops. This right here is all one line.
Okay.
Yeah. And then that's been, oops. And then that's been summarized down to this line. And then that with this line. And ultimately, that line. Okay. All right. I was thinking we would get done a little earlier. We didn't. That's okay. So pay attention to your signs. So basically all I did, and going back up to here, is this. Coefficient. Number read out of the back of the book. Coefficient. Number read out of the back of the book. Coefficient. Number read out of the back of the book. Could find it in the back of the book, but I should know it's 0. And then I just got to make sure that I pay attention to signs. So a positive and a negative makes a negative. A positive and a negative makes a negative. A positive and a negative makes a negative. But there's a negative in between there. So pay attention to your signs. So basically, you got everything for your next test. That's all you're going to have. You have one of these problems. You're going to have to write some equations. You're going to have to do one of those kind of Hess's Law problems. And I don't think I have this test scheduled until next Wednesday or Thursday. Okay, so there's a lot of time to get through it. We'll do a little new material before that, but the new material is pretty soft. Good?